Bismillahirrahmanirrahim. This is another video about FET, and here we'll be solving self-bias and chapter questions 6 and 7. Primarily we'll be solving 7, but for this we need to solve question 6. Just repeat some of the things. This is the main circuit for FET self-bias. And as we had discussed that we remove the capacitor for DC biasing, and also IG current is 0, therefore the voltage drop here will be 0. And so the circuit will look like this. And from here we, by KVL, we write the equation. Okay, ID and ISS will be same because IG is 0. And this equation is called the network equation. VGS plus VRS equal to 0, and therefore VGS is equal to minus VRS, or VGS equal to minus IDRS. This we have already learned, and this is called network equation. Now the networks are group of interconnected devices. Basically there are two equations, there are two plots that will be discussed. One is called the network plot, another is called the device plot. So when we say device, we only mean the FET. When we say network, we mean the whole network. So this is the network characteristics, and this is the device characteristics. And as we have learned, we superimpose the both, and then we'll find the question point IDQ and VGSQ. This is plotted with the Shockley's equation, and this is plotted with the network equation. Now, the question number 6 says that for the self-bias, figure this, sketch the transfer curve of the device, and then superimpose the network equation on the same graph, determine ID, VQ, and VGSQ, and calculate these 4 parameters. I'll hurriedly go because we have done exactly same type of a question in my previous video. The transfer characteristics of the device. We know we have learned that it can be plotted from the Shockley's equation, and by taking various values, VGS is equal to 0, VGS equal to VP, VP by 2, VGS equal to 0.35, we find the value of ID, and then we can plot. This graph is plotted like this for various values, like when VG is 0, this, then IDSS is 10 milliampere. Similarly, these 4. So this is the device characteristics curve. And then we'll plot the network characteristics curve, which is like this, which can be plotted from here. So you again here also will put couple of values. For example, when ID is 0, then VG will be 0, so we are here. Then when ID is 5 milliampere, then from here we can calculate it to be minus 3.75, so minus 3.75. So we mark a point here, and then we can connect this with the center of the 0. This line is our or this plot is our network plot. Now we have 2 plots to determine IDQ and VGQ. As we have discussed earlier, that we have to superimpose the network graph on the device graph. So superimposing, we get this point, and this is the Q point. So let's use the graph given in the book. So this is Q point. And from here, you can see that IDQ is approximately 2.7 milliampere here, and VGSQ from here is minus 1.9 volt. So this is part C. Then part D, we have to calculate this 4 parameter VDS. This one we have calculated in earlier videos as well. VDD, this. minus the voltage drop here and the voltage drop here. And so solving, we find 11.93. Remember, ID we are using, the IDQ that we have calculated is 2.7 milliampere. Similarly, VD is this here at D. It is VDD minus this voltage drop, IDRD. So VD is 13.95. Then VG obviously 0. And Vs is the voltage here, Vs at the source. So ISRS or IDRS, it is 2.3 volt. So we have found all the parameters required for question number 6. Now, what question number 7 wants is that determine IDQ for the network of figure, same circuit in question 6 using purely mathematical approach. That is, establish the quadratic equation for ID and choose the solution compatible with the network characteristics and compare the solution obtained in problem 6. So let's do that. We start with the Shockley's equation, obviously. Now VGSQ is ID minus RS. This is the network equation from here. So for VGS, we can put IDRS from here, VGS or SQ or minus IDRS. The VP remains same. And this we can open the whole square. Now we multiply by IDS. We get this term. Rearranging this, ID comes here. And taking common, this one is with ID square, ID minus I, we take common from here. So this term is the ID and then IDSS. And now if we put the values, we know IDSS is 10 milliampere, RS 750 ohm, VP is minus 4. So putting all these values and solving, we get this relation here. And now you can solve this by the quadratic formula and you will get this answer. But let's try to solve it using the calculator. Okay, so here is the calculator. It is always best practice to clear it before we start. We put shift and this is clear. 9 is saying clear all 3. Yes, equal sign and AC. So it is all clear. And now we'll move into the equation mode. So press mode switch. This 5 is for equation. So 5. And our case, it is a quadratic equation. So 3 is our option. And now it is asking the value of A, B, C. Now, if you remember the quadratic equation, we have like ax square plus bx plus c. So this is our A. So let's put it 351.56 equal. So this is entered. Now this is our B minus 4.75 entered. And C is 10 milliampere, which can be written as 0.01 ampere. So we add this. So all 3 values are entered. Now we'll do the calculation or solve. So shift, solve, and then we press equal because it's saying solve equal sign. So this is the first value that we are getting is 0.0109 or we can say it 1091 milliampere. So 109 milliampere is one value, which is we are calling x1. The other value, again we press equal sign. So this is the second value, 2.6 milliampere. So 2.6 milliampere. So these are the two values that we will get by using the calculator. Okay. Now we will neglect the first one, because ID cannot be greater than ISS. So the ISS value in our case is given as 10 milliampere. So the drain current cannot be more than that. Therefore, we have put in a cross. So we'll take this value 2.6 milliampere as the ID. Now this value we have obtained through the equation. Now we have to compare with the question number 6. And in question number 6, we found IDQ to be approximately 2.7 milliampere. So our answer is very close. I hope you have been able to follow this. Please let me know through your comments. Thank you.